Okay, so question number 49. A projectile is launched from a point x equals to 0 and y equals to 0 with velocity 12I plus 49j meters per second at t equals to 0. A. Make a table listing the projectile's distance r from the origin at the end of each second thereafter for 0 less than or equals to t less than or equal to 10 seconds. Tabulating the x and y coordinates and the components of the velocity vx and vy may also be useful. So basically, what I did was, I wrote down the initial velocity for the x direction and the y direction, which was given in the problem, just in a different form. So I put it in x is 12 and then y is 49. So x is 12 meters per second, y is 49 meters per second. So that's just a very simple graph. So basically we're trying to find r, and since we have this graph, we know that if we use Pythagorean theorem, r squared would be equal to x squared plus y squared. So r would be the square root of x squared plus y squared. So x and y, of course, we're referring to the distance and not velocity. So in order to find the distance, we're just going to use the equation, which is like the first one, or the second one, x equals to vit plus 1/2 at squared. So we're going to copy that down, which is here. And then we simplify it for x, because you know that in the x direction there's no acceleration, right? So this entire thing would just be 0. So if this entire thing is 0, then we know that the equation to find the displacement in the x direction would just be x equals to velocity initial x times t. And since we already know this, so t is the only unknown variable. And in the y direction, we use the same equation, but in the y direction we have acceleration due to gravity, which we know the value of. So for this equation, the only unknown is also t, time. Since the question A is asking us to make a table for t from 0 seconds to 10 seconds, which basically means that t is the x that we're trying to find. And obviously we can do it the hard way and do it by hand, which is what I did here for like one variable, which you substitute. 12 is the 12 meters per second. You substitute it here, and then there's the t, and then you since the t is 1 second, because at 0 it's just 0, since it already told you that it's starting from origin. So at 1, it would just be 12 meters squared plus this entire thing, which represents the displacement for the y direction. And then you simplify it, and then you get 45.7. But that's too hard to do because it's way too time consuming, because we'll have to do it for 10 times. So it's an easier way is to just plug it into a calculator, which is what I did. So just to show you guys, the first equation is the equation to find the displacement in the y direction. So you can see all we did was we plugged in velocity initial for y, 49, and then the t, time, would just be x, since we don't right, that's what's changing. And then 0.5 gravity is negative, right? Because our frame of references, we're going up, that's positive. So gravity is acting down, so that's negative. And then t squared. And then for this one, the second equation, you don't have to do it, but I'm just putting it here so it's clear. So 12 meters per second times t. So 12x when you put it in the calculator. And the black one, the third equation is basically our equation to find r, which is what we're trying to find for 49a. So all you have to do is x squared plus the square root of x squared plus y squared, which you can see here. That's x squared, and this whole thing is our first equation, which is y. And then if you scroll over, you can see that this is squared 2. And then now all you have to do is you change your window, because sometimes your window might not accommodate everything. So after making sure your window and everything works, you graph it. So that's our first line, that's our second one. We're looking for the black line. The black line is what we're trying to find. So now that we've graphed it, we go to second table, and then see x, that's time, and then ignore these two colored ones because they're just there for your information. And y3 is what we're trying to find. So basically, from when x is equals to 0 to 10, this is our value for r here, displacement. So you copy that down to your table. So at 1, it's 45.704, etc., etc., and 10 is 120. So copy those values down. That's your answer for 49A. Okay, for 49B, observe that the projectile's distance from its starting point increases with time, goes through a maximum, and starts to decrease, which is right? As you can see, the maximum value is at 137.89. So it increases, and then after 6 seconds, like at 7 and 8, it kind of gradually decreases, which you can also see from the graph. Prove that the distance is a maximum when the position vector is perpendicular to the velocity. So what I basically ended up saying was that if the angle is not perpendicular to the velocity, then you know that some component of the velocity would be either going for or going against the displacement vectors, like x and y component, which would make it, when you add them together and perform this, if either of those is not at its maximum, then r wouldn't be at its maximum. So basically, you can only have the maximum when the angle isn't interfering with any of the components of r, which is when the angle is 90 degrees. And then for C, determine the magnitude of the maximum distance. Explain your method. That's just really easy, since referring back to our table from question number 49A, this is our table, right? So maximum displacement is just maximum r, so the biggest r. So where do we have our biggest r? We have it here, 39.89. That's our biggest r, so that's our biggest displacement. So it happens at around 6 seconds, so that would be our answer, 137.89 meters. All we did was we graphed it, and then we looked at the table, and we found the largest displacement, because it increases, it hits that point, and then it decreases. So that's question number 49, everything, yeah.